Good morning, Year 12. We're going to start the Year 13 section of Additional Pure today. I've emailed you one of these documents, which is all of the Additional Pure module, showing what's in the Year 12 and the Year 13. So everything in green you'll already have done. And the stuff in blue is what we are going to start on this year. You see that some topics, for example, sequences and series, majority you've already covered, and there's just one last little bit that we have to do in Year 13. As you kind of look down towards the end, lots of the calculus, surfaces, partial differentiation, lots of that calculus there is going to be done this year because it relies on new calculus that you're just about to be doing in normal maths. So we're going to start with number theory. Number theory, a great topic to do at the moment because it contains lots of kind of little self-contained things. Not too tricky, it's just kind of very different maths, isn't it? It's very different maths to what you've done, so it means it's an ideal topic to do now. I would really recommend, if it's at all possible, to print this out. I assume that you're still keeping up organisationally. You know, put this in a file, have a file, put this in here, and then the stuff that we're going to be looking at today. I've emailed you this document as well. Like, have those notes, print them out, put them in the file, and it just means that you're going to be on top of things when we do all come back together at school. The more organised you can be now, the easier it's going to be for you. Right, so to start with, you, of course, have done this relatively recently, so it's not going to be a huge effort for you to kind of look back at that. It's more, I want to talk about kind of methods and a couple of little things, a couple of little technical aspects. So if you pause the video, please have a go at this now. Okay, so I don't think you'll have had many issues in the actual solving of it. The method used in the online textbook, and I think the method that you'd have looked at first for Mrs. James, the division method. So we need to think of all of the things equivalent to 11 mod 23. So if I add 23 onto 11, get 34, add on another 23 is 57, keep on adding, we get to 80, and of course 80 is significant. 80 is significant because that is divisible by 5. So that's how we can rewrite that. So that is just equivalent to this. Both of those divisible by 5, so we can say that x is congruent to 16 mod 23. Now, if you'd have put that in your exam, you'd have probably just got 3 marks out of 4 or 2 marks out of 3. There is one thing in particular, as mathematicians, we always worry about, or we should worry about. It's dividing by 0. Because we're dealing with this modulo arithmetic, you know, odd things can happen. We might kind of have zeros where we might not kind of expect it, and that happens if these two things here have got common factors. If these things here have common factors, then, you know, odd things can happen and we could end up dividing by 0 when we weren't expecting it. So if you're using this division method, the way to make sure that you get the full marks is by this clause here. So what I would do at this stage here, I would say that as HCF of 5 and 23 is equal to 1, then I can do that division. So that thing there is something that's crucial to the whole argument, and I'm sure, you know, you'd have talked about that a little bit with Mrs. James, but just, you know, make sure, if in doubt, just kind of write it down. Having 2 things that are co-prime is crucial to a lot of the number theory stuff. There is a second method, and having looked at exam papers and mark schemes, this is the method that I think is kind of the more mathematically accurate. I think some people marking the exams kind of were a little bit sniffy about this method. Of course, there's nothing wrong with it as long as you state that that is a perfectly, you know, technical and valid method to use. The inverse method goes about things slightly differently. So we start off with that. And If I multiply by 14, it might seem a little bit random why 14, but that gives us an answer of 70, which is just one above a multiple of 23. So if I multiply the initial congruence by 14, I get 70x is congruent to 154 mod 23. And now I can make the numbers smaller in a similar way. You know, I made the numbers smaller there by dividing, but here crucially I'm not dividing. What I'm doing is I'm reducing it mod 23. So 70 is equivalent to 1 mod 23 because of this kind of result here. And 154, well, if I take away lots of multiples of 23, what's it going to be? 115 is subtract another 23. I think, does that get me to 16? So reduced by mod 23, that gets me just 1x. Reduced by mod 23, that gets me 16. Exactly the same answer, but this method, if you're like a super pure number theorist, that's kind of what you would do because it avoids that dividing by 0. If you are wanting to kind of talk about what this actually is here, why this 14 is significant, we'd call it the inverse of 5 mod 23. Because when we multiply 14 by 5, that gets us 1 above a multiple of 23. It can be a bit of a faff finding this, but of course you could set up kind of, lists in your calculator to help you find those. Just to clarify though, I'm going to be using this method as we go through because I think that's the one that you will be more familiar with. Okay, so on to the year 13 work. So in year 12, you were just solving a single congruence. What we've got here, 2 congruences. So I have 2 congruences to be satisfied, 2 mod 5 and 3 mod 6. And of course, you know what that means. That just means I'm looking at solutions of the form 2 plus 5a and solutions of the form 3 plus 6b. So what we can do is we can just make a list. Write down all the numbers that satisfy 2 above a multiple of 5, 7, 12, 17, and so on. And then if we do the second congruence, 3 above a multiple of 6, 9, 15, 21, and so on. And of course, it's a bit like finding an LCM, isn't it? We have got, a common 27 there and there. But actually also, if you look further down, we've got a common 57. So we have a common solutions, 27, 57, and I'm sure you're all, can establish that if we just repeat that, we'll get another one at 87 and so on. This is the key thing here, it's repeating every 30. If it's repeating every 30 and the first solution is 27, of course, the solution to the congruence, x is congruent 27, 130. That 30, that 30, of course, is because it's the product of 5 and 6. So we look at the initial question, 5 times 6 is 30, so with respect to solution mod 30, and that 27, well, do your list, that's just where the first solution occurs. So by this listing method, it's a good way of working out the simpler ones. Got a second one here. X is congruent to 3 mod 4, x is congruent to 5 mod 6. So still, nice small numbers. So let's try listing it to see what we do. So we've got 3 above a multiple of 4, 3, 7, 11, 15, and so on. I have then got 5 above a multiple of 6, 5, 11, 17, and so on. Look at the common ones. There are a few more here. I've got an 11 and a 23, a 35 and a 47. First solution is 11 and it repeats every 12. So here it's not as simple as 4 times 6. But of course there's something that 4 and 6 do that 5 and 6 don't. 5 and 6 for coprime, there are no common factors. Here, the HCF of 4 and 6 is equal to 2. So it's not simply 4 times 6, it's 4 times 6, but it's been reduced by that factor of 2, which is 12. And I'm sure lots of you kind of said at the start, well, it's just the lowest common multiple, isn't it? So 12 is the lowest common multiple of 4 and 6. So I've summarised this here. To find the solutions of simultaneous linear congruences, you can find the first solution just by listing. If the HCF of the individual moduli is 1, then the modulo of the solution is just the product. If it's not equal to 1, then the modulo of the solution is the LCM. The LCM, but weirdly, we kind of tend to use that statement instead. It just means exactly the same as the LCM, but we like this kind of product MN because it makes it similar to that above case there. And HCF, well, we're always writing down, we're always considering HCFs when it comes to number theory. So we'd use that expression rather than the simpler LCM. So that method is kind of great. I mean, I called it inspection there, but it's also a listing method. But if the numbers are more awkward, so if you don't find your initial solution within the first 10, 20, I mean, if you've got 13 and 27 in there, you're going to be going an awful long way before you get a common solution. And I know you can put the lists into your calculator, but if you want a method that you can get 3-4 marks for an exam, you need to be writing things down. So whether it's kind of writing down all the numbers in the list, which you don't want to be doing if you're having to list 30, 40 numbers, or of course an algebraic method. Trying to find an alternative method that works not just for the simpler ones but works for the more awkward ones should be our aim. So this is where, please, if you're able to print these out, if you write your solutions, if you kind of write notes just as you would do in lesson. So we have got our 2 congruences here. It is the same as the one that we've just been looking at, the first example that we started with. I can use a little bit of the inspection method and just, even just in my head, but I like to write it down. The HCF is equal to 1, so I'm expecting solutions mod 30. Okay, they're co-prime, so I just do 5 times 6. Now, rewrite congruence 1. Rewrite it as an algebraic statement, as an equality rather than a congruence. So x is equal to 2 plus 5. Let's use A. So 2 above a multiple 5. I'm going to call that statement star because I want to refer back to it. I'm going to substitute this into the second one. So just as you would do for simultaneous equations, that is a very common method of solving simultaneous equations. So instead of the x there, I'm just going to replace it with all of that. So 2 plus 5a is congruent to 3 mod 6. And then solve this congruence. So you've solved congruences like this. Well, I say last year, but in the year 12 part of the course. Subtract 2 from both sides, so 5a is congruent to 1. Mod 6, I'll use the division method. I want to keep going 1 above a multiple of 6, so it's a multiple of 5, 25. 25 is it. So 5a is congruent to 25 mod 6. I want to divide, but whenever I do that, I just need to comment on the 5 and the 6 are co-prime. So that means that I can divide both sides by 5. So I get that a is congruent to 5 mod 6. Rewrite that as an equality. A is equal to 5 plus 6. So I need to use another letter here. Let's use B, say. Now I've got an expression here for A, but I've also got A in this starred expression here. So what I'm going to do, I'm going to substitute back into star. Put that into there, and I know that X is equal to 2 plus 5 lots of A, and instead of A, I'm going to use that. Expand those brackets, simplify. I've got 2 plus 25 plus 30b. So that's 27 plus 30b. And that, of course, means multiples of 30. So that's my modulo, and that is my initial solution. So 27 mod 30, which, of course, confirms and agrees with that listing the inspection method. Okay, so of course it's it's an algorithm, and it is a little bit clumsy, but this is something that's always going to work. It's always going to work when you've got particularly odd numbers. So please, I know some of you are going to be, well, I can just see what the answer is. You need to practice this method. Practice this method so you can do it when the numbers do get quite horrible. Before we move on to the next one, though, I just want to show you what happens if we start with congruence 2. So what I did on that attempt, I started off with rewriting my first statement, but instead, and it might kind of go against your instincts, but I think as soon as you've seen what happens, it's, oh, this is quite nice. So I should really be using 2 different letters, but sorry, I'm committed now. X is equal to 3 plus 6a. Substitute that into congruence 1. So X, which I've rewritten as 3 plus 6a, is congruent to mod 5. Now, what happens here, in particular with this bit here, that modulo that we're dealing with is always going to be smaller than that. So now it means that I can just reduce it. I can say that 6a is equivalent to 1a if I'm talking mod 5. And it means that I don't have kind of this awkwardness here where my modulo was bigger than my multiple of a, so I had to go through all the multiples. I know it's not a huge deal, but it just simplifies it. And sometimes my head does hurt kind of finding all the equivalents, just adding on numbers can be a little bit tedious. So by doing this, I can say that 6a mod 5 is equivalent to just 1a, or just a. At the same time, what I'll do is I'll subtract 3 from both sides to get minus 1 mod 5. And then I'm dealing with mod 5, so add 5 onto that, so a is equivalent to 4 mod 5. So that stage is simpler. Write that as an equation, so a is equal to 4 plus 5b. And then I'm going to put that in place of a there. So now substitute back. X is equal to 3 plus, using that statement, 6 lots of 4 plus 5b. Expand the brackets. 6 4s, 24. 6 5s, 30b. So again, I get 27 plus 30b. So X is congruent to 27 mod 30. Not mod 30, mod B, mod 30. So tip. Always do that. I'm going to do that every one from now on. So if you start with the congruence that has the greater modulus, it kind of goes against your intuitive. Normally we kind of do like doing the smaller numbers, but it will simplify the solving stage. Okay, example 2. Again, this is the second one that we did at the very start. X is congruent to 3 mod 4, X is congruent to 5 mod 6. I'm going to start with the bigger of the 2 moduli, so X equals 5 mod 6. Rewrite that as an equation. Substitute it into 1. So into 1, that one there. So on the left-hand side, instead of x, I'm going to have 5 plus 6a, and that is congruent to 3 mod 4. What I'm going to do now is I'm going to reduce that by mod 4, so that will go down to a 2a. I can subtract 2 from both sides. Don't really like that 2 being negative. Of course, add 4 to both sides. 2a is congruent to 2 mod 4. Now, this is something possibly that you may have forgotten. When you've got a common factor in all those 3 bits, of course, you can just divide through completely, including in that modulus. And that is, of course, because this statement here is saying 2a is equal to 2 plus some multiple of 4. So let's say 4b. If you are ever given a statement like that, of course, you can just divide, can't you? I can just divide and say a is equal to 1 plus 2b. That means that this statement here is equivalent to a is congruent to 1 mod 2. And it's easy to forget, isn't it? It's easy to forget when, in other occasions we can't do that. So whenever you've got a common factor in everything, you can do that division. Compare if that had been a 5. 2a equals 2 plus 5b. You couldn't then halve it to keep everything at integers. So I've got a is congruent to 1 mod 2. Well, I've already kind of got that written there. So I've got an expression for a, which I can now substitute that. So substitute that, I called it star, didn't I, on an earlier question. So let's put that star in there. X equals 5 plus 6 lots of 1 plus 2b. Expand out. 5 plus 6 plus 12b. 11 plus 12b. So x is congruent to 11 mod 12. Okay, there we go. Confirms the inspection method. Just take care, just remember that statement, that little bit there. Okay, third one. Slightly more interesting, slightly different. We've got a 7 and a 15. That 7, that 15, if you double 7, you get 14, which is 1 away from 15. That kind of implies that if you were writing lists, you'd have to go a fair way up. And we're expecting, of course, as the HCF of 7 and 15 is equal to 1, our solutions are going to be modulo 7 times by 15, which is 105. And actually that's reminded me, probably should have commented on that there because it was, even more significant. If at the start I'd have remembered just to check out that HCF of 4 and 6 is equal to 2. So that means that the modulus of my solutions is going to be not simply 4 times 6, it'll be 4 times 6 over 2. And if I'd have done that first, it would have given me a little bit of a heads up about that, wouldn't it? It would have reminded me that there would need to be dividing by 2 at some stage. So, yeah, I've got it there. It's good practice just always to comment on your HCFs. So, as I said here, first simplify each congruent. Essentially, it's solving, isn't it? So if I start off with 3x plus 1 is congruent to 6 mod 7. Subtract 1 from both sides. 3x is congruent to 5 mod 7. I need to look for something... Oh, 12 works, doesn't it? 3x is congruent to 12 mod 7. So 5 plus 7 gets me 12. And now, because the HCF of 3 and 7 is equal to 1, I can divide by 3. So that gets me that x is congruent to 4 mod 7. If I do the second one, 7x minus 2 is congruent to 7 mod 15. 7x is congruent to 9 mod 15. So I want 9 above a multiple of 15. that's a multiple of 7, so 15, so that's 22, doesn't work. 39 doesn't work. 50, no, it doesn't work. 69, no. Oh, 84. 84 works. So 7x is congruent to 84 mod 15. I need to make the HCF comments. Those are co-prime, so I can divide by that 7. So x is congruent to, if I divide that by 7, I get 12 mod 15. So now this is what I'm going to refer to as equation 1, and that's what I'm going to refer to as what congruence 2. Start with number 2. Number 2 tells me that x is equal to 12 plus 15a. Substitute into 1. 12 plus 15a is congruent to 4 mod 7. Solving that, oh well, this is very nice because I can reduce that mod 7. 7 times 2 is 14, so I can just write that as a single 1a. I could kind of reduce that before I subtract, or I could subtract it. Should I just subtract it first? 4 minus 12 is negative 8. Mod 7. Add on 7, negative 1. Add on another 1. Gets me... sorry, I'm hearing a knob buzzing. I think it's from elsewhere in the house. Right, I'm going to carry on. So A is equal to, so if I add 14 on, I get 6 mod 7. A is equal to, I want to write it as an equation, 6 plus 7b. Put that back into that statement there. X is equal to 12 plus 15. 6 plus 7b, 12 plus 90 plus 105b. So I get 102 plus 105b. So x is congruent to 102 mod 105. Okay, got one more to do. One more, a wordy one. Find the largest 3-digit integer that leaves a remainder of 5 when divided by 8 and a remainder of 4 when divided by 9. Of course, this can be easily transferred into congruences. And you can imagine this being, you know, a kind of a maths challenge question, can't you? Or one of those questions about you've got 2 clocks and one chimes after so many hours, one chime, and when do they first chime together? It's, you know, this kind of problem. So I know that that first one is just equivalent to 5 mod 8, and the second one is equivalent to 4 mod 9. Number 1 and number 2. So I'm going to start with 2. Number 2 implies that x can be written as 4 plus 9a. Substitute that into 1, and I know that 4 plus 9a is congruent to 5 mod 8. Solving that is easy. I have got a very nice 1 above a multiple of 8, so that's just going to be a single a. I'm going to subtract 1 from both sides. Oh, and that's just a 1. Mod 8. So a is equal to 1 plus 8b. Now, pop that back into that expression there. Hence, x is equal to 4 plus 9, 1 plus 8b. Expand, plus 72b, 13 plus 72b. So x is congruent to 13 mod 72. Oh, but I've got to do the largest integer. So if I go back to this statement here, I know that my solutions are of the form 13 plus 72n, where n is some integer. And if you just go through multiples of that, what am I going to get? 3-digit number? The largest 3-digit number. So 72 times by 15. Oh, that's a bit big. 1,080. So 72 times by 14. Oh, that's 1,008. So 72 times by 13. Yeah, that'll do it. So when n is equal to 13, that is going to be 13 plus 72 times by 13. 949. Okay, so hopefully you'll agree that's not too tricky. Questions on the next page. 3 of which are just basic congruences, and another 3 where you have to firstly solve the individual ones first. As I said up here, try the algebraic way, do the algebraic way, because when it gets to the more awkward ones, you need to be able to use that method. Okay, thank you, and I will see you tomorrow for the second lesson on simultaneous congruences.